we have something, we have to somehow stick something in for HF. I'm fine with Giovanni saying that the height is 0 at the bottom, but the big question is why? Why is the height 0 at the bottom?
We defined it actually.
Yeah, because Giovanni said so. So this is 0. Final height equals 0 because Giovanni said so. You're mighty, you're powerful. Don't give credit to someone else when you made it so. All right, so we are now left with a much simpler equation there. Oh, I put it away, that's why I couldn't find it. So we have G times H initial equals 1/2 VF squared. I want to figure out what the final speed is, what the speed at the bottom. So we have VF is equal to the square root of 2GH initial, which is the square root of 2 times, let's put it on Earth, 9.8, times the initial height of, well, because of Giovanni, this is 50 meters per second squared. And we end up with the square root of 980, which is 30 something. What'd you get, Giovanni?
31.3.
31.3. Units? Yep. That's how fast he's going at the bottom. Questions up there, so I'm going to change the problem slightly. All right, here we go. So, our speeder goes all the way down to the bottom. Liked it so much, he goes back up to the top to do it again. What he doesn't realize is that there was a cave-in while he was making his way back to the top. There's now a giant hole there. He starts skiing down. When he gets down here, what is his final speed?
0.
Just before he hits anything. The answer is easier than you might think.
9.8.
2.
31.3.
Give me the units, too.
Give me a second.
Yeah, absolutely. Nothing has changed in our problem because what we are finding is speed. We are not finding velocity. The velocities are not the same, but the speed is the same. Nothing has changed in, well, I erased it, but everything still stays.
That's gonna trip me up because like it says V or final velocity, and since we've been doing cake formulas, we think of. Or actually, no,
Oh.
it doesn't have a vector symbol though.
Yeah, that's why it's speed. It does mess some people up because they think V immediately think velocity and not think V with a vector is velocity. V scalar is speed. Now, in case you were worried about our skier, there were clouds, cotton balls, and kittens down there. He did not land on any kittens. If there had been cats and he landed on them, we would care. But kittens, we're not dealing. Any cat people in here? That's insulting. Cats.
I haven't yet.
Do you mind if I make fun of them? Go ahead. Cats. All right. Anyway, so the kittens show him another way to get up to the top. So he works his way up to the top and he gets up here. While he's working his way back up this time, two things happen. One, there's a big snowfall and this all fills in. And two, as you would expect on a ski slope, a giant spring has been installed down here.
Are the kittens still alive?
Yes, kittens were not hurt during the during this problem.
Cave kittens.
It was monitored by the SPCA, so kittens are fine. Still not sure why the kittens were down there, probably put there by the cats, and which is why cats are. Yeah, I said it. So the question now is, how he skis down the ramp, how much will the spring compress? So I'm introducing another force. This is an ideal spring. It is also a conservative force. We will get into springs in more detail near the end of the course. But the formula for the potential energy of an ideal spring, that's a lowercase k, delta x squared. This k is known as the spring constant. It is basically a stiffness constant. The larger the value, the stiffer the spring is. Now, an example of a value of k, the one that we'll use for this is, we'll just say 20 newtons per meter, which means that the spring, it will require 20 newtons of force in order to compress or stretch it 1 meter. If I want to compress it 2 meters, it'll take 40 newtons of force. Let's go with the pattern here. If I want to compress it 3 meters, how much force is required?
You said 360?
If I want to stretch it 3 meters, how much force is required?
60?
Yeah. Units?
Newtons?
Yes. So, he's coming down, he hits the spring. The amount of force that the spring exerts varies, because it starts out basically sitting there, fat, dumb, and happy. No force at all, but the more it gets compressed, the more force is being applied. Delta X. How much spring is displaced from equilibrium? So using the, not an ideal spring, but small adjustments, you can get pretty close to an ideal approximation here. So that's an equilibrium position right there. If I pull it down, so whatever height that, whatever position that is, if I pull it down, then the distance that I've pulled it from its equilibrium position, that's delta x, or if I push it up, how far it is off of where it was in equilibrium, that's delta x. It's squared, so it could be plus or minus, but you're squared. So we start out with all this gravitational potential energy and no kinetic and no elastic potential energy. As he goes down, his gravitational potential energy goes down, his kinetic energy goes up, and then you got that small little hill, and then at the bottom, the gravitational potential energy is down to 0, thanks to Giovanni, and the kinetic, it's all kinetic energy. Then he hits the spring, so we have all this kinetic energy at this point. He hits the spring, and so now the spring is going to be increasing in potential energy, and his kinetic energy drops. So we're going from gravitational potential to kinetic to elastic potential. Setting it up, again, energy is conserved. I have energy initial equals energy final. I have K initial plus U initial. Actually, U sub G initial plus U sub S initial, because I have two different types of potential energy, because I have two different conservative forces in play, equals K final plus U G final plus U S final. At the very beginning, which of these is equal to 0? Let's go to the next step. So 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared is equal to 1/2 mv final squared plus mgh final 1/2 k delta x final squared. Okay. What's 0?
Wait, what is G?
What, little g?
Yeah.
That's the acceleration due to gravity. We're similar on Earth. 9.8 meters per second squared. I will need to eventually give a mass to the person, because mass does not cancel out this time.
So
But what? Sorry?
is this like the formula for like how much potential energy is in the spring as it's fully,
Yeah.
what did you say?
As it compresses, more and more energy is being stored in the spring, which is potential energy. And so we're trying to figure out how much it'll compress. So what equals 0? We can get rid of, actually 4 terms.
Initial speed,
Pardon?
the initial speed,
Initial speed indeed. All right, so 0 because the initial speed equals 0. All right, what else?
Height?
Which one?
5.
Yep. Thanks, Giovanni. That's 0 because the final height is 0 meters. Okay? 2 down, 2 to go.
and initial displacement.
The spring's just sitting there. Delta x equals 0. Initial. And one more.
The
Final velocity is 0.
Because when you hit the spring, you're moving, but the spring is going to keep compressing until you stop moving. It's going to be that turnaround point. And so this has to be 0 also, because that will define the maximum compression. So I'm left with just mgh initial is equal to 1/2 k delta x squared, final squared. So delta x final equals the square root of 2 mgh initial over k. K, 20 newtons per meter, m, let's make them 70 kilograms. Which I think is US adult average, or US adult male average. So the square root of 2 times 70 times 9.8 times 50 divided by 20. 2 comments about ideal spring. 1, ideal spring doesn't have mass. Any mass you have to attach to it, and it's usually a point mass at this point. And also, an ideal spring will not interfere with itself. If I take this is clearly not ideal, but if I push, I compress and compress, at some point it's going to run into itself. Ideal spring's not going to have that issue.
So it can get infinitely shrunk.
Yes. Or if you want, it's infinitely big. So you work through that, you get an answer. What would the units be? What did you find?
Meters.
Yes, you found how far it would be
Oh,
compressed,
right.
something meters. Anyway, I know you have to go, Logan. So we did centripetal motion lab last time, right? Or was
Yes.
that? Yeah, that was this group. Yes.
Maybe there's energy.
Yep. Okay.
Huh? That's not a bad piece.